minus I.
I regret. I'm going to write that over here because I don't want to write the other one again. That's okay. Because I want to write the answer down here. I mean, not the answer, but the... I'm trying to avoid writing that again.
Yeah.
So this minus this plus minus that, right?
Yeah.
Gives us what? Well, the sine pieces cancel, right? And we get minus 2 cosine.
Do the sine pieces cancel? I don't think they do. Because you get an I. You minus an I. So that'd be minus cosine minus I sine.
Oh.
And that would be I cosine minus, or plus sine.
Oh.
So it's minus cosine minus I sine. I cosine
Oh.
plus sine.
All right, fine. Let's...
Maybe I did something wrong.
Well, I'm trying to multiply by this, right?
Yeah.
This is...
Oh, I think I know what we did wrong. That's dividing by minus I, not multiplying by minus I.
Oh.
So that
All right. Forget this.
No, so that'd be 1.
I'm going to do this. All right, so this is minus I over minus 2I. Minus 1 over minus 2I, right? Minus I over minus 2I, 1 over minus 2I, right? Which is what? 1/2. This is I over 2, rather minus I over 2. And this is 1/2. And this is I over 2, I believe. Do you agree with that? Or
Cosine. Oh, I just corrected the green matrix, and it made it works out if you fix it. So that green matrix is 1 minus I, 1I, and
yeah.
So that one becomes 2 cosine now.
Okay, so we multiply this times that. What do we get? No, I hope not.
Make sure we go. Keep that the same. Cool. This becomes minus I sine. That becomes. Yeah, I think so.
See, because I got a half cosine and another half cosine here.
Yeah.
Oh, this one's 0?
No, I'm talking about the top one.
This one? That one?
Yeah.
No, I don't think that's 0. This is 1/2 cosine plus, see, I squared is minus 1. So it's a half plus a half. I get a cosine theta. And I get a plus I over 2 sine theta, and then another plus I over 2. So a half plus a half is I sine theta. And the lower, the 2, 1 component here, I'm hoping stuff cancels because, yeah, check it out, right? I've got cosine theta times a half, and then I times I is minus 1. So I get minus a half, half plus minus a half, and the sine terms also cancel. I get 0.
Yeah.
And then when I work through this over here, which would be, let's see here. All right, 1/2.
Alright, so okay, good. Yeah. Yeah, I got a 2 up front. Okay, yeah. I'm with you. I think that should be cosine theta minus I sine theta. Or is it sine theta minus cosine? Yeah.
I don't know without looking.
Either got cosine theta minus I sine theta or sine theta minus cosine.
It's probably too.
It's one of those two.
It's probably too small to see now. Let me zoom in.
So sine theta minus I sine theta.
To remember to zoom back out once we're done with this a little bit. So that better be 0. I get a half cosine.
Yeah, I think that one's 0.
Minus a half, and then minus I over 2, and then plus I over 2, 0.
This is sine theta. That's minus I sine theta though.
So you notice we've got,
Yeah. Let me show you real quick. That times that. Cool. And then that's the bottom. Cool. And yeah, this one's about. So this would be cosine. Minus
this
I
is
sine theta.
this is wrong. Let me.
Yeah. This should be cosine, 1/2 cosine theta minus I sine theta. And
Plus I over 2, right?
yeah, there it is. Yeah, and then you should get
So minus I squared over 2, which is a half. Half cosine plus half cosine.
You get 2 cosine minus 2 sine I sine theta.
Minus I sine theta, right?
Yeah.
All right.
That's what I got. Nice.
Now this is e to the I theta, e to the minus I theta, as we had wanted. So what could not be diagonalized over the reals now has been diagonalized over the complexes. So this is complexification at work. Okay, so the end of this story is ultimately what's called the Jordan form.
Yeah.
And so this, this matrix actually is already in what I would call the real Jordan form. So how to say this? Well, I don't want to do all that today.
Okay.
So we'll come back to the real Jordan form and the Jordan form and the rest of this story. I just wanted to get us started on this, yeah?
Yeah.
So we've done that. Whew, that was a bit of a calculation. So let me me show you about, let's talk more about tensor products and vector spaces. So this is from section 11.2 of Thumb and Foot. But so he has got a proposition 15 and a proposition 16. Proposition 15 is, I think, essentially the complexification. So he's got W, a vector space. I'll just write it up here. Proposition 15. He starts with a W, n-dimensional vector space over F. So W over F. The dimension over F of W is n. All right. And then he says, okay, well, suppose that, K is an extension. Let me back off my double Fing here. I'll just do single F. There we go. Oh no, what am I doing? Double F's fun. I'll do double. I haven't done double K in here yet, have I? So K over F. So suppose K is an extension of F, yeah. Then so here, we'll suppose W1, Wn basis for W. Then if we do K tensor W, and this has, he says one tensor W1, one tensor W2, one tensor Wn basis over K. So here, let me call this V. So here V has the K dimension of n. So let's see here. So here's what I teach in linear algebra. I suppose I have like a vector space W over the reals, right? With basis, let's say W1, W2, Wn, right? And then I call it the complexification of W, right? But pretty sure that that's just C tensor W. This has basis, what's the basis? 1 tensor W1, 1 tensor Wn. All right. Over C. Okay, so the main issue here is how do you get the complex scalar multiplication on your complex vector space? Let me stop and explain how that works here. So, all right. So what's a kind of typical thing in this tensor, C tensor W? It's something of the form, I gotta explain how to multiply A plus IB, right? I think if I define it for a simple tensor, then we can extend from there. So the simple tensor looks like X plus IY, right? Tensor W. well, I'll just say tensor wj, right? I'll just say tensor w. I just leave it w. Fine. How does that work? The way it works is ax. So I multiply this time. I multiply this times that, right? Audric, I multiply this by that. Just regular complex number multiplication.
Okay.
Remember the tensor into it has that. You can bring the scalar either into the first or into the second. We can't do the second here though because the second's a real vector space, and I don't have a way of multiplying a complex number by a real vector directly here. So I'm not sure I'm really using the properties of tensor products right now as much as I'm defining the scalar. I'm defining scalar multiplication on C tensor W. Well, anyway, let me not think too much. Thinking will get me into trouble here. AX minus BY plus I times AY plus BX, yeah?
Yeah.
All tensor W.
Yeah, I was gonna ask, like, if this was just say, like, C plus ID, or C is equal to, or then just,
Yeah, I should have got my notes. I think I'm... Man. Well. Okay, I think I know the problem. In terms of my concept here, yeah. What is it? So if this is V, right? To really describe this, the multiplication, the scalar multiplication, I shouldn't just look at it in the way I'm doing. I need to think about what does an arbitrary thing in V look like, you know? I think that this calculation is fine. It's just not helpful. It's not helpful for the question I'm trying to answer. So let's think about it. What does an arbitrary thing in here look like? It would be something like, let's say Z equal to, the sum. I equals 1 to n. Ooh, I is be a bad choice. J equals 1 to n. And let's say x sub I, j rather, plus I y sub j, right? Multiplying what? 1 tensor w j, yeah? And that, yeah, this was the point. Sum j equals 1 to n. xj 1 tensor wj plus the sum j equals 1 to n of I. Well, this is the thing, is do I want to do, I'm not sure where I want to put the I. I'll do it this way, yj I tensor wj. I mean, you could like that. Now, this is a nice formula because this shows you that V has, basically we can use 1 tensor W1, I tensor W1, dot, 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 1 tensor Wn, I tensor Wn, right? How many things are in there?
N. Oh, 2n things?
2n, right? So this is 2n linearly independent over R. So the complexification is a real vector space itself of dimension twice what you started. So that's one way to look at this calculation. Another way to look at it would be so I guess this is the way I do it in linear algebra is I don't write 1 tensor wj and I don't write 1 tensor this or this. I just, for here, I just write wj. I just write wj here, I write I times wj there. So if you just drop the tensor with 1, that leaves you with the notation I use in linear, for what it's worth. So here's my definition in linear algebra. If I have a plus ib, and I multiply it by x plus iy, here x and y are in V, and x plus iy is in the complexification of V. So that's like one of my claims is that any vector in the complexification can be written as x plus I times a real vector plus I times the imaginary vector. In terms of the more honest notation here, that is, so that is this breaks up into, see this is the sum j equals 1 to n of like xj, well, excuse me, good grief. I just see what I'm supposed to write as I'm, so here it is. So I'll bring the sum, the thing is I'm going to bring that sum into the second tensor, and this is 1 tensor the sum over xj wj plus I tensor sum. This is where my mental block was. Well, one of my mental blocks. So my point is that what I've written, these guys, right?
Yeah.
This is, x in W, and x in W, and this is a y in W, right? And so any vector in the tensor product of C and W can be written as 1 tensor a real vector plus I tensor a real vector. So this is in some sense, I'm letting x plus iy as be a stand-in for 1 tensor x plus I tensor y. But the way I define the complex multiplication, scalar multiplication in linear, is just to say, well, you just multiply like you'd expect. So if I have a plus ib, and I'm multiplying it by, 1 tensor x plus I tensor y, my rule should be what? My rule is this, I guess putting that back into the other, that's circle 1. 1 tensor ax minus by plus I tensor bx plus ay. I'm sure I'm making things more complicated than they need to look like it here, but I'm mostly doing that for I'm trying to make contact with a linear algebra course that you never took from me, which is really kind of stupid, but sorry. But anyway, yes, the complexification of a real vector space is a complex vector space, which can be viewed as a 2n dimensional real vector space over that. Now, then the natural, if there's some things we can look at here, right? Like for the one we just had, if we have, this t of, xy. Well, instead of writing cosine sine, let's write a b minus ba. All right. If that's the matrix if that's the matrix of t, that's manifestly the matrix of t from R2 to R2, right? Then we can define the complexification of t, all right, which I usually use like a t sub c, to just be the same thing essentially. So sorry, let me just make my life a little bit easier here. T of v, right, equals to v, and so I'm just going to call that m. So Tc of, what's the typical vector in the complexification of R2? It has something of the form like v plus iw, yeah? So it's just going to be m times v plus iw, which of course is mv plus imw. So this is a definition for T sub c, okay? My question is, what's the matrix of T sub c? With respect to, like, if I, with respect to a basis beta, let's say. And what would be an interesting basis to take? Like, so T sub c, right? And I mean as a real, so there's different things you can go here, right?
Yeah.
Do we mean the matrix as a complex mapping? Do we mean it as a real mapping? See, if we're thinking of this as, a mapping of a 4-dimensional real vector space, the basis for that would be like E1, there's different choices. I could either do this. There are many choices. Here are 2 natural choices. Or I could do this, yeah? So let's do you pick it. Which one do you want to do?
I'd rather keep the eyes together.
Keep the eyes together? Okay, so this will be, so we do T of E1 Now, what is that?
That's 1, 0, 0, 0.
Mm-hmm. Yeah, it's 1, 0, 0, 0. Well, it's not 1, 0, 0. It's A, right?
This is 0, B, 0, 0.
Yeah. I mean, because it's really ME1, right? Excuse me, like here, it's ME1 plus I times 0, right? I mean, so then, yeah, like you said, 0B, 0, 0. That when I plug IE1 into here, I get V is 0, W is E1. So I get I ME1. So I'm looking at the coordinate vector of ME1 is blah, 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 blah. Oh, my bad. Oh, Audric, I'm sorry. ME1 was not just A0. ME1 is A minus B. ME2 is BA, right? Column 1 and column 2 of M. So I should have had A minus B for this one and BA for this one. And
For the next one,
so, yeah.
like 0, 0, A, B? A minus B?
Yeah, let's see, so we plug in IE1 into this, we get,
Yeah, you flip it right, then you go to the bottom. There's like 0, 0.
yeah, I'm sorry, we have what, IE1 minus IBE2,
Yeah.
coordinate of that, so that's, like you said, 0 copies of this, 0 copies of that. Dummy, there was an A here. So we get an A here,
Minus B.
minus B.
I think the other one's BA.
Right, and then the last one would be,
BA. So you get a diagonal ace.
well, it's not diagonal, right? What we have, though, is something, while it's not diagonal, we do have a nice pattern. We have M, M.
0, 0.
So that's not an accident. Like if you have a linear transformation, right? If you have like t going from, say, for lack of let me be confusing. Let me go from B to V, right? And then suppose you have t of x is equal to mx, right? And then you were like to define, t sub k is the kification of t, which is a mapping from k tensor v to k tensor v, right? And suppose this is over f, right? And if the dimension of k was equal to, let's say, s, all right, then, and if the basis for f was, let's say, like, basis for k rather, I need some other letters. Let's say F1. How about K1? K2. KS, yeah. Then you could use a basis for K tensor V. Would have basis you could do like, and suppose that V has basis V1 through Vn, yeah? So you could use this as like K1 tensor V1, K, and so forth and so on, Ks tensor V1, I'm an idiot. K1 tensor V1, dot, 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 K1 tensor Vn, I'm trying to stick with your basis choice, yeah?
Yeah.
And then you do with K2. Eventually you get the K2 tensor Vn rather. And then, yeah, and eventually you get the Ks tensor Vn, right?
Yeah.
That would be a S times n, an Sn dimensional vector space over F.
Yeah.
And if you do this, if we order the basis like this, right? And you look, and so I'm supposing that this I have neglected. So this is the basis of T with respect to the basis of T with respect to my V1 through, I'm gonna call it beta. I'll find gamma. Gamma basis here. Gamma is V1. All right, fine. Then if I let beta be this basis down here for the Kification of the map, then the matrix with respect to that is going to be, and I'm supposing this matrix is M again, then this has matrix of this guy with respect to, I'm calling this beta, by essentially the same calculation, M, right, like that. Where did I put my phone? Oh, that's good. Well, that's random. Somebody I know is on Signal. I never really use Signal. I use Signal mostly because sometimes my brother will pick that up, but he won't pick anything else up.
Signal?
Signal.
What is that?
You don't know about the Signal?
No.
Ah.
So when you like erase your phone number?
It's like an anonymous. Was it anonymous? I don't know. It's one of these privacy, helpful texting things. That, of course, if you talk to other people, all the central banks are behind it anyway, so it's still spying on you or whatever. I don't know. I can't keep my conspiracies straight. And the thing is, conspiracies aren't really conspiracies anymore. They're just reality you haven't been informed of yet. But now that matrix, so here's some things I want to share with you. A1, direct sum, A2, direct sum AS. So that actually is the direct sum of matrices. We can define a direct sum for matrices like this. Audric is just like, is it block diagonal?
Yeah.
So you just, sometimes we start linear algebra by telling students things they can't do sometimes. We're like, you can't add matrices of different sizes. Well, yes, you can. You just do something like this. But the other thing you can do, and definition, is if we have A and B, R by N, and S by M. So A is R by N. B is S by M. Then you can define the Kronecker product or tensor product of A and B A tensor B. It is a RS by NM matrix. All right. Where you can define it in terms of blocks. It's an R by N block matrix. R by N block matrix whose ijth block is alpha ij times b. Now here, he's using alpha ij for the components of A. So my typical notation would be to use aij for that, right?
Yeah.
So specifically, this is looking like A1, 1b, A1, 2b. How big is A? R by N, so AR. That's 2. That's 2, 1. I'm a dummy. 2, 1. 2, 1. I need to teach linear. I'm getting rusty. It's not good. A2, 1. B. A2, 2b. AR, 2b. AR, how many we got? N.
You lost me. We got A2, 1B in 2 places.
That's right, because that was supposed to be... like I said, I need to teach linear. I'm going to teach it to somebody. This is apology to my children I'm going to teach them linear. I teach it to somebody, so these are my children. No one else is available. No, he's linear. But that's the tensor product of two matrices, and this. Okay, so this is also the matrix of the linear map on the tensor product, in the sense that if you have, let me try to tie this together here. If he talks about phi going from v to x, and again, this is page 421 of Dummett and Foote, psi going from w to y. Right. So, like, essentially, if you don't mind, I would rather not. I don't know. See, this is the thing. I want to not talk about the basis, but I don't know if I can get away with it without talking about the basis. But here's the thing. We can talk about psi, tensor, phi, tensor psi. This is going to be a mapping from v tensor w to x tensor y. All right. And how does that work? Well, so here's the formula. This is phi tensor psi acting on, let's say, v sub I tensor w sub j, where the little v's and the little w's are a basis for v and w respectively. Well, this is just phi of vi tensor psi of wj. So it's just very natural rule. And if you excuse me. So if you look at the natural tensor bases for this and that, just ordering things in the natural way, then the matrix of phi tensor psi, it ends up being the Kronecker product of the matrix of this map with that map. Now, the tensor, the Kronecker product here, that's like the same Kronecker as Kronecker delta. I can't remember how to spell the stupid thing. Maybe this. This is a Kronecker product. That same pattern ends up showing up when we look at the Jordan block decomposition. So we'll need this formula again when we get to that. So, but anyway, I think this is interesting in that there's also a tensor product for matrices. You can build bigger matrices from smaller matrices, and it's also interesting in that it's an associative product. So if you were to look at like the Kronecker product of A, B, and C,
yeah, you can
either way, yeah. So. All right. So let's see, what else was I supposed to tell you about? Let me erase all this here. So have we ever talked about the dual space before?
Dual space, maybe in differential geometry.
In differential geometry, we did, yeah, we talked about it there. But let's revisit that dual space. What's dual space? So if you have V, vector space over F, then the dual is homomorphisms, really linear transformations from your vector space into the field. So let's see here. So a standard example of this would be if I have V equal to Rn, right? What's a dual vector there? Well, if I have alpha in V dual, what does it look like? Well,
Alpha's a linear transformation.
mm-hmm. So I have alpha of like, let's see, a typical vector in Rn looks like what? Some I equals 1 to n of, let's say, xi ei, right? And so that's the sum I equals 1 to n of xi alpha of ei. Which you could write as like alpha 1, alpha 2, alpha n times x1, x2, xn. Here, of course, I'm letting alpha sub j equal to alpha of ei, yeah, ej rather. So what's the matrix multiplication going on here? We've got 1 by n times n by 1, 1 by 1, right?
Yeah.
So that's really a dot product, right? But from this, we get the statement, oftentimes statement you'll hear, for Rn column vectors, the dual space is row vectors, which is not strictly true, right? But to each linear transformation from Rn to R, you can write that by uniquely by giving a row vector. So the matrix really, what this is really is the standard matrix of alpha with respect to the standard basis, you know? So, I mean, a quicker way to do this calculation would have been alpha x. Oh, well, that's the standard matrix of alpha times x. And the standard matrix of alpha is a row vector. So, every, yeah. So, is the dual space isomorphic to the vector space? You say no?
Yeah, so you're asking if there's as many linear transformation as there are vectors in the span?
Right.
I don't think that's true.
Are there as many, is the dimension of row, like, are there as many independent row vectors as there are independent column vectors of the same number of components? I mean,
Say that one more time. Is there as many row vectors as column vectors?
yeah, is the dimension of n-dimensional row space the same as the dimension of n-dimensional column space? I mean,
I have to go back and look at that one thing.
so what's, I guess my question is, what's a basis for our 1 by n?
What's the basis for our 1 by n?
Right, we can just use these guys, right?
Yeah, just E1 and 2.
Right. Well, they're not, I mean, in my notation, they're not E1. This is E1 transpose. This is En transpose,
Yeah.
you know? So it turns out in the finite dimensional case, yes, the vector space and the dual space are isomorphic. However, in the infinite dimensional case, it's not the truth. It's not the case. There are many more, well, they don't have to be isomorphic in the infinite dimensional case. So like when you study functional analysis, they won't just look at all linear functionals, they'll look at like the ones that are bounded, because otherwise there's too many of them. So, but if we suppose the dimension of V is finite dimensional, all right, then if, you know, beta, let's say V1, Vn basis for V, then you can define beta dual to be, let's say, V upper 1, V upper n for V dual. And here's how we define it, where Vi on Vj is Kronecker delta Ij. All right, and then Vi is a mapping from V to your field, all right? So you basically definition, and we use a little, there's a theorem of linear algebra, right? If you define a linear transformation on a basis for a vector space, there exists a unique linear extension, right? So here's a pretty typical, a potential subject to GRE question based on that. So suppose you had T of 1, 1 equal to 2, 3, and you had T of 0, 1 equals to 8, 9. Find T of x, y. Given that T is linear. See?
X cubed y squared.
No. It has to be a matrix. I mean, if this is linear, it has to be something of the form like it has to be linear in x and y, yeah? But the point is that this question makes sense because 1, 1, comma 0, 1 is a basis for R2.
Yeah.
Now, this right here is actually very telling because this tells me if I write T, the standard matrix of T, right? that tells me that the second column has to be 8, 9. Because this is T of E2.
Yeah.
That's column 2 of the standard matrix of T, yeah? But then I still need to figure out what this A and B are, yeah?
Yeah.
So I know that T on 1, 1 equals to 2, 3, yeah?
Yeah.
So now I know that A plus 8 equals to 2, and I know that B plus 9 equals to 3.
B is 6, minus 6, A is minus 6.
So you say this is A is minus 6 and B is
Minus 6.
minus 6. And now you can try it out. So just double check, right? 1, 1 times this gives me 2. 1, 1 times that gives me minus 6 plus 9, which is 3. Great. And if I do 0, 1, I get 8, 9. So there you go. That's the matrix. So this is an illustration of that theorem. If we have the values of a map given on the basis for a vector space, and we're given that that map is linear, game over, that defines the map, because we can linearly extend off the values of the basis. So my claim is that if you define V upper I like this, well, first of all, that uniquely defines V upper I. But second of all, that this V upper I, the so-called dual basis, is a basis for V dual. So here's why it's a basis, right? So if I have alpha in V dual, right? And I let alpha act on X, that's alpha acting on the sum I equals 1 to n of X sub I, VI, V lower I, right? And, oh man, I've worked myself into the corner. So suppose we have X is X sub I VI, right? And then we let E, good grief, we let V upper J act on X. What do we get?
Oh, you get like X, you get all the XI's and BI's except for when I is equal to J. You get a 0 on that term.
Right, so this is by construction, Kronecker delta ij, and so that summation just drops back to X sub J, right? Which means that when I'm calculating alpha acting on X, I'm really just calculating alpha acting on what? The sum I equals 1 to n of Vj, V upper J, good grief,